Hey guys, welcome back. I'm going to be talking about the lab part now. So this is experiment 1. We're going to talk about the theory that goes with chemical equilibrium. Like I've said before, there is a lab video that goes with that to walk you through exactly what you need to do, because we aren't in the lab together, so I don't have an opportunity to walk you through that when we're in the laboratory. All right, so I've done that way. This experiment is on pages 13 to 18 in the lab manual. It contains a pre-lab summary, post-lab spreadsheet, and notebook, in addition to the ALEX. So I added the ALEX later than everything else because people wanted simulations to go with these experiments. That's only a 10-point part of this. It's part of this grade, so make sure you do that as well. So let's see. We know that the equilibrium can be described by K, the equilibrium constant, and that's products of a reactants raise their stoichiometric coefficients, where concentration represents molar concentration, moles per liter, and P or R represents the stoichiometric coefficient of the component. From that, I can see that if K equals 1, I have roughly the same concentration of reactant and product. We talked about that. K is greater than 1, then my products are greater than my reactants. And if K is less than 1, the reactants are greater than the products. If my Q, the equilibrium or the reaction quotient, so not the equilibrium condition, but the reaction quotient, whatever condition I'm in now, is equal to K, then I'm at equilibrium and everything goes forward and back just as it's supposed to. If my Q is greater than K, then my concentration of my product is too large, and so I'm going to favor the reverse reaction. Sorry. If my Q is less than K, then my reactant is too large. So I need to go forward to get rid of it, okay? But here's the thing. How do we study this in the lab? How do we know that this is a constant? How do we know that all of this stuff is the way that it is? And how are we going to be able to see that in the lab? Well, turns out we have ways that we can do that. One of the ways that we can do that is to be able to measure the concentration at specific times, okay, so that we can see like how long it takes for things to happen, but that's related to the kinetics, and that's not what we're interested in right here. What we're interested in is knowing how much we have. Now, we have a reaction that we can monitor, because this reaction, Fe3 plus SCN minus, going to FeSCN2 plus, that's a colored product. So if I make a colored product, then I can use a spectrophotometer to measure how much light goes through that solution. So as the concentration goes up, less light goes through it, so that percent transmittance goes down, and that means that my concentration is higher. We actually have a direct relationship between absorbance and concentration. That's Beer's law, and it's in the appendix of the lab manual. It says that absorbance is equal to the molar absorptivity times the path length times the concentration. The path length is 1 centimeter, because our cuvette that we use is a 1 centimeter square cuvette. So it's a 1 centimeter path. That means it drops out. That molar absorptivity is actually the slope of the line of a calibration curve for this. So if we have a known concentration of this thiocyanate that we can plot, and then we take the absorbance of that, we should be able to get a linear plot of what that concentration curve looks like, and it is linear. Okay, so that's what we're going to do in the first part of the lab, is generate a calibration curve for that. In the second part of the lab, we're going to make some stuff where we don't necessarily know what those concentrations are, take the measurement to find out what they are, and then use that to be able to do some things with it, okay? So in order to generate that calibration curve, we need to be able to know exactly what that concentration of FeSCN is, 2 plus is. In order to do that, we're going to manipulate Le Chatelier's principle. And so we're going to have a huge excess of the SCN minus that we add to this thing by making that concentration very, orders of magnitude bigger than the iron. So the iron, being the limiting reagent, that will determine exactly how much iron thiocyanate I make. And so I know that concentration, so I can take the absorbance measurement and then generate a calibration curve. And that is what has been done in the first part. So you were given data for that first part. And again, watch the lab thing to figure out where all of that works and how all of it goes. Okay. We'll then be able to get a plot of A versus C. That's in the spreadsheet that you've been given. Okay, once you have that, then you can take the percent transmittance for your unknown solutions, where we don't have a large excess of either of these components, to see what is the concentration of the FeSCN at equilibrium. If I know what that concentration of FeSCN is at equilibrium, and I know that I'm reacting Fe3 plus SCN minus to give me FeSCN 2 plus, then I can calculate it. We have initial concentrations because we know what we mixed. So there was amount of A, there was amount of B. This is how it's in your lab manual. It says you use this much of this. And then initially we have none of that. We know that there's a change. I have a minus X here. I have a minus X here. I have a plus X here. That is supposed to be an X here. And then at equilibrium, we're going to have A minus X, B minus X, and X. Okay, so if I find the concentration of the FeSCN 2 plus through the calibration curve, then X is going to be equal to that concentration. All right, so I will know what that concentration is and therefore what the value of X is. I will know how much A I started with and how much B I started with so that I can actually calculate how much of each of those components I have. And then using K is equal to that X over A minus X times B minus X. If I know all three of those values, I can calculate K. Okay, so that's what we're doing here, is we're finding those values to be able to calculate K. All right. We do this with all of these wonderful experiments. We set all of this up. You will be asked to show a number of different calculations. So you're going to make a dilution of the initial iron. And we'll use M1V1 equals M2V2, which is good for dilution of solutions, to calculate the new concentration of the Fe2 plus. Fe2 plus dilute. So you'll need to show that. That solution is then going to get used to make your calibration curves. So that molarity, M1 molarity, is going to be used to make your calibration curve. And again, we want a large excess of the SCN minus, so we always have the same concentration and the same amount of that being added. We also have the same amount and same concentration of the HNO3, the nitric acid, which all of this stuff is soluble in as a background. So that's always going to be the same. What's going to change is the amount of the dilute iron solution that you will add. And so we will need to calculate exactly what the concentration is for each of those. That's fine. You can do that. You only have to show that calculation once. You will then have to show how this calculation is done in the spreadsheet. So it's done for you in the spreadsheet, but you have to show me one of them so that I know that you know what's going on. A couple of things in that spreadsheet: make sure that you've checked all of the percent transmittance values that you were given and that they match, and that the concentrations that you have calculated are the ones that are in the spreadsheet. Okay, because they may not be. Right? So you'll need to put in your percent transmittance. That will then generate a calibration curve for you. Again, the slope of this line is the molar absorptivity of that species. You don't really need to know that, but that is how that works. Okay, so you'll need to calculate what the concentration of the dilute solution is, and then what the concentration in each beaker is. All right, and that you will need to do. And then here, you're going to put in your percent transmittance for your second set, where we're looking to find K, all right? So when you do that, you'll need to know what the concentration of Fe to start with and SCN to start with. And those are the values that you need to verify to make sure that those numbers are right. You'll put in your percent transmittance, it knows the molar absorptivity, so it can solve for the concentration of FeSCN. Once it's done that, it can do subtract that from the Fe and subtract that from the SCN, and then calculate Kc. Okay, so it's going to calculate Kc for you. Now, what you'll see in this and what you'll see in your own data is that they're not always the same. They should be. If they're not, why are they not? Give me some speculation as to why they might not be. And that speculation should be based on what was done in the laboratory. So there are a couple of things that you could be looking at that could have happened. Obviously, we could have had contaminated solutions. We could have had mismeasurement of things going in to make our standards so that they're not exactly the concentration they're supposed to be. You may see that this is slightly deviated from an actual line because there is only a finite region over which this is linear. So it may be a deviation in that. Think about things that may be coming up in this. My point here is not to point out where people have done stuff wrong. That's not my point. I don't care that things got done wrong. What I care about is, can you critically look at the experiment as it was done, as it was described to you, and look at, are there things that might have gone wrong? Are there things that I could check to see that they were done correctly? Are there things that I could change next time to see if I get the same values? This is part of doing experimentation, because if we get into the lab and it doesn't do what we're expecting it to do, then we have to figure out why. Is it something that I did wrong, or is it something that I need to change some parameters of my experiment to be able to test further? So all of those things are critical. And my thesis was actually based on a negative result, meaning that it didn't match anything that it was supposed to match. And I had to do an enormous amount of testing to prove that none of these factors were what was causing that. Okay. So again, negative results are important because we know what it's not. But we also need to have some idea, where do we go next? And we need to be able to look critically at what we've done. Okay. So you will have your pre-lab and summary. I walked through that in the lab video, so you'll have to fill that out. You'll have your information for table 2. You'll have the discussion and reflection that goes in the summary. And of course, you need to explain in your own words Peirce's law. You can Google that. You need to give some explanation of why or why not it does support it. And of course, the question becomes, is this a good line? And if you zoom in a little bit, what you'll see is that the R-squared value for this is 0.9814. Now, R-squared is a statistical measurement of how well the data points match the line that we drew. So we draw the line of best fit through those data points. And that should give equal variation on both sides. But if it's, if there's a lot of variation that we have to deal with, then we're going to get a low correlation. So that R-squared value will be low. And the question becomes, is that a good fit? Do you think, qualitatively looking at it, that the way that those data points sit on that line is a great way to do that? Or is it maybe not the best line? And that's something that we need to be able to comment on in terms of, because if it's not the best line and we're basing all the rest of our data on that, then that may not be the best way to do this. We might need to make better efforts to get a better calibration curve so that we can eliminate that as part of our problem. Okay? So that's the kind of stuff you need to do for that. I have talked about all of this stuff in fairly good detail for the lab portion. Now, don't panic, okay? I have a lot of students who come into this lab and they look at all this stuff that they're being expected to do, and it's really different than what the expectation was at 110. We are expecting you to expand your horizons. So you need to have taken all of the information from 110 and be able to apply it here. And we're expecting you to be able to look at now not just one system, but multiple systems, to look at, are these conditions right for this, or are they not, i.e. Q versus K? it's a lot more, and it's a lot more mathematics too. We're doing things that are a lot more mathematical this time than we did last time. And we also need to use the stoichiometry from last time to be able to do this. So don't panic. It is not something to panic over. If you don't understand some of the stuff that we're talking about, if the lectures are not helping you, then contact me. It is my job. It is what they pay me for, is to help you understand. So if I can help you by talking to you outside of this, then that's fine. I feel a little weird about having online students because I don't get that daily interaction with you to see where you are and are not understanding. Because that's what I have with my own student, my in-person students, is I get to hear those things and see those things. And that's helpful to me. So we don't really have that here. So if you're not getting what you need from these lectures, let me know. Please, don't think that you're bothering me. You're not. You're absolutely not. So these more practice things, I'm definitely going to put the answers on D2L. If I can get caught up, I'll try and record video for it. If they're on D2L and you need an explanation, a walkthrough of how I got that, reach out. Don't wait for me to do it. Just reach out and say, hey, can you do this for me? And I'll be happy to do that one. Okay. There are going to be additional things here. There are in-class questions. Those are meant to be straightforward. What is this? What is this? What is this? And then there are questions that I write that are similar to how I do my tests, that some of those are very straightforward, some of them are not. Most of those questions are present just so you can see how I will ask those questions. Okay? So I think that's everything I have at this point. I hope you don't have any questions, but if you do, please let me know, and I will get this posted as soon as possible, and let's move on. We'll get to the next one. All right, guys, I'll talk to you later. Thanks.